So let's consider this problem. If you look at this, maybe you can recall a theorem that says if D is the greatest common divisor of A and B, of course A and B are integers, then there exists some integers x and y such that ax plus by is equal to D. Okay, maybe we can use this theorem, but the problem is D here. So in this case 14 should be the greatest common divisor of 1976 and 533. However, that's not the case. This is 14 is an even number, but 533 is obviously an odd number, so 14 cannot divide this number. So we cannot use this theorem directly. And of course, the if so for logically speaking, if D is not the greatest common divisor of A and B, it does not necessarily indicate that there exists no integers x and y such that this holds. Okay, so we cannot say this. It's contrapositive is okay, but inverse of this statement is not necessarily true. Nevertheless, let's first find out the greatest common divisor of this number and this number. So we apply the Euclidean algorithm. So 1976 equals to 533 times, according to my calculation, it should be times 3 plus 377. And now we divide 533 by 377. Then, according to my calculation, this is times 1 plus 156. Then we divide this number. And 156, that is times 2 plus 65. Then 156, 65 times 2 plus 26, and 65, 26 times 2 plus 13, and 26 is 13 times 2. Therefore, 13 is the greatest common divisor of 1976 and 533. So, we are sure that there exists some integers that satisfy this. 533y equals to 13. Now compare this with the given equation. So the right hand side is 14 instead of 13. So suppose we are sure that there exists some integers such that this is satisfied. Okay, so suppose if we have integer solutions of the given equation. Suppose there exists x prime and y prime, which are integers, such that 533y prime is equal to 14. Now compare these two equations. So equation 1, we are certain that it is satisfied. Equation 2, we don't know if there are any integers x prime and y prime that satisfy this equation. But let's say let's subtract equation 1 from 2. Then we have 1976 x prime minus x, 533 y prime minus y equal to 1. Okay, so if there are integers x prime and y prime such that this is true, then x prime minus x is an integer, and y prime minus y is also an integer. So if we put so there should be integers such that this is satisfied. Okay, but now the right hand side is 1, and 1 divides both this and this, right? But so this means if 1 is the greatest common divisor of these two numbers, then there exists this and this. But that's not true. Of course, we know that the greatest common divisor of these two numbers is 13. Actually, we cannot use that theorem here, this theorem, but we can use the converse of this theorem that says if d divides a and d divides b, and x and y are integers that satisfy x plus by equal to d, then d is the greatest common divisor of a and b. Okay, so we can use this theorem, and 1 divides both 1976 and 533. So these conditions are satisfied, and x prime minus x, y prime minus y, they are integers. So these are satisfied, and we are assuming that this is true. If that's the case, then 1 at the right hand side here, 1 should be the greatest common divisor. Okay, but that is not true. So 1 is not the greatest common divisor of 1976533. So this is a contradiction. So there was something wrong in our assumption, and the only assumption that can be violated here is this. So therefore, there are no integers x prime and x prime minus x and y prime minus y that satisfy this equation. No such integers. But we know that x and y do exist from this. So therefore, there are no such integers. Let's x prime and y prime. So there are no solutions. And we're done. So let's consider this problem. This is just checking the definition of equivalence relation. Okay, so S is the set of points on the circumference of a circle. So let's say this is the center. And P and Q are defined to be related if there is a diameter. So if this is P, and if there is a diameter, that is a line that passes through the center of the circle. So if there is so P and Q are on this line that passes through the diameter, then they are defined to be related. Let's say let's show this is an equivalence relation. First thing we need to check is reflexivity. So if P is a point on this circle in this circumference, then of course we can draw any diameter, and P is just the same point. So obviously P is related to P itself. So the reflexivity is satisfied. And two, suppose P is related to Q. Then we have a line that passes through the 3 points P, Q, and the center. Okay, if that's the case, then Q is related to P because there is a line that passes through Q, center, and P. Therefore, the symmetry is satisfied. Now, uh, suppose P is related to Q and Q is related to R, say. Then, so if P is related to Q, then uh, they they are on the same line that passes through the center. And Q is related to R, then R is either equal to P or Q. So this may be R or this may be R. Okay, therefore P is related to R. Okay, if R is equal to P, then by the first point, P and R are the same point, so P must be related to R. If R is same as Q, then of course because of this, then P is related to R. So either case P is related to R. Therefore, this relation is an equivalence relation. Next, consider this problem. So D is an integral domain. So that means it's a ring that is commutative and with identity element and without proper divisors of 0. Okay, so in that case, the polynomial ring D of x is an integral domain. Let's prove this. So since okay, so let's say if A of x A of x and B of x are polynomials that belong to D of x. So let's write A of x as A0, A1x, and so on up to am x to the power of m. And B of x, B0, B1x, and so on, Bn x to the power of n. Okay, and we assume that the 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 coefficients of the highest degree term are non-zero. Okay, and since D is already commutative, then we have ax times bx is equal to bx times ax. So this is okay. And so commutativity is fine because because uh, D is commutative. We have this. If you want to see in detail, for example, a k x to the power of k times bl to the power of xl is equal. So if we multiply these two polynomials, we have something like not like this. We have something like bl x k plus l. So since a and ak and bl, this part is commutative. We have bl ak, and of course this is just addition, so it's commutative. L plus k. So this holds for every term that appears in this product. Therefore, we have this. Okay, and the identity element. Let's say the identity element of D is 1. Then we can define the identity element of D of x as the constant 1. And by this, so for example, 1 x is just 1 a0 plus 1 a1x and so on. And since this 1 is the identity element of D, so this is equal to a0 and this is equal to a1 and so on. So is the identity element of D of x. And the last thing we need to show is the absence of proper divisors of 0. So suppose, so we are assuming this. So a of x is not 0 and b of x is not 0. Okay, so a of x times b of x contains the term am times bn x to the power of m plus n, which is non-zero because D is a commutative ring. This is not 0 because am bn is not 0 for any non-zero a m and bn. Therefore, a of x times b of x is not 0. Therefore, there are no proper divisors of 0. Therefore, no proper divisors of 0. Therefore, d of x is an integral domain. We are done. Okay, so let's consider this set of complex numbers, and cosine 2k pi over 3 plus I sine 2k pi over 3. This is using Euler's formula. This is equal to exponential of I times 2k pi over 3. Okay, and this is equal to, so let's take this k out, so exponential of I 2 pi over 3 everything to the power of k. Okay, so therefore let a be the constant exponential of I 2 pi over 3. Then S is a set of powers of A. Right? Now, if we multiply A twice, so A squared is exponential of I 4 pi over 3. And if we cubed A, then we have exponential of I 2 pi, which is 1. Okay, so that means all the higher powers, so for example a to the power of 4 is equal to A, because it is a to the power of 3 times A, but a to the power of 3 is 1, so this is equal to A. And a to the power of 5 is this, so this is equal to A squared. So there are only 3 distinct elements in this set. That is 1 and A squared. So we have 1A squared. So if this is a group, then its order is 3. Okay, so let's show this is a group. And to do that, it's a multiplicative group, so we make the Cayley table. So 1A squared, 1A squared. So 1 times 1 is 1, 1 times A is A, 1 times A squared is A squared, A squared, and A times A is A squared, and A times A squared is A cubed, which is equal to 1. And A squared times A is A cubed, which is equal to 1. And A squared times A squared is A to the power of 4, but that is equal to A. So this multiplication table, Cayley table, contains only 1 A and A squared. So that means closure condition is satisfied. Closure. It's satisfied. And associativity is of course satisfied because all the elements are only powers of A, so associativity is satisfied. And identity element is of course 1. And the inverse element. So 1 times 1 is 1. So the inverse element of 1 is 1. And A times A squared is 1. So that means A inverse is A squared. And so A squared inverse is A. So similarly, so this times this is 1. So for every element, there exists an inverse element. So inverse element, inverses, they do exist. Therefore, S is a group. of order 3. And we are done. Okay, GL to R is a set of matrices that can be expressed as this: A, B, C, D. A, B, C, D are real, and the determinant is non-zero. So determinant is AD minus BC in this case. So determinant being non-zero means these matrices are invertible. Okay, so this is a big hint. So let's see if this set satisfies all the axioms of a group. First of all, if A and B are elements of this set, then AB is a 2 by 2 real matrix. And the determinant of AB is, as you learn in linear algebra, it is the product of determinants. So because of this, determinants of A is non-zero, and determinant of B is non-zero. Therefore, this is non-zero. Therefore, AB belongs to this set. Okay? So the closure condition is satisfied. And associativity is true because matrix multiplication is associative. Multiplication is associative. So associativity is okay. And the identity element is the identity element. Of GL to R. So that means IA equal to AI is equal to A. And by definition, all elements of GL to R are invertible. So the inverse elements are already there, always there. Therefore, GL to R is a group. And next, we show that this subset is a subgroup of GL to R that is also abelian. So that means commutative. Okay, first of all, we need to check this set is indeed a subset of GL to R. Okay, so that means this is 2 by 2 real matrix, that's for sure. And is this non-singular? Yes, the determinant is always 1 times 1 minus 0, so that is 1, so it's non-zero. Therefore, this is a subset of GL to R. Okay, now we check the subgroup criterion. So suppose we have 1A0, 1 and 1B0, 1 that belong to H. And if we multiply these matrices, we have 1 times 1, A times 0, that is 1, and 1B A1, so A plus B here, and 0, 0, 0, 0, 1. So, so the product belongs to H, subset H. So the closure condition is satisfied. And what about the inverse element? Actually, from this product, we can immediately see what the inverse element is. So the inverse element of 1a 0 1 should be 1 negative a 0 1. As you can see, so if you replace b with negative a, then this will be the identity matrix. So this is the inverse element, and which is also an element of H. Therefore, by the subgroup criterion, H is a subgroup of GL to R.